about large-scale Django lessons. So it will be a collection to analyze your systems and perhaps architect your monolith in the best way. So most of the things come from practice, recollections of some blogs, and also our own experience in monadical working in these kind of big systems. So I hope you like the talk. So the first thing is like obvious architecture, it's hard. So that's the first thing that you should take away. So why architecture is hard? So you usually don't end up receiving this answer. You only get like, there's a bunch of trade-offs, there is a lot of books that you need to read and consider, there is a lot of techniques. But why is it that it's hard? So I'm a physicist by training, so let me try to answer this question from a different approach that you might be used to. So that's from the physics. So I will do it using the concept from cybernetics. So cybernetics has many definitions, but one of those is the art of effective organization. And that certainly will be useful for organizing your computer architecture. So for this matter, allow me to introduce the definition that it's called variety. So variety measures the number of possible system states. So you can consider a system by its state. So let's just take a simple system like a dice. So you will have only like 6 states, one for each of the faces. If you have a 2 dice system, you will have 36. There will be a combination of one of the states from one dice with all the other combinations from another. So that's the concept of variety. A software system, believe it or not, can also be analyzed like this. It's also a system that has a certain number of states. So a software system interacts with an environment that is usually a complex environment. So it ends up acting like a controller. The software system receives some input. It does some assumptions over the inputs that it allows into the system, and it also has some design decisions for that matter. So how it can interact with the environment, that's called a design decision, or some conditions or preconditions over the inputs. It has also some certain numbers of states. So trivially, you can imagine that per each combination of the inputs, you can have one of those states. So the software system in general, it's a controller. Let's try to understand this with a very simple system that it's like a thermostat. So let's imagine a very simple thermostat that it's a system that turns on and off certain controller to control the temperature. So this system, as the thermostat, it only has 2 states. The minimum interaction that it can have with the environment should be accomplished through only those states. There are no other measures or other like smaller quantities that it can detect, only these 2 states. So why is it important, and how this connects to software systems? So there exists something called the first law of cybernetics. So let me explain that. So the complexity of a control system, in this case our software system, must be equal or greater than the complexity of the system it controls. That's a fundamental principle that you cannot overcome. When you start with that, you start to understand why computer systems are difficult. You always need a certain representation of the number of states to be able to act upon the environment. So for a system to be stable, the number of states that its control mechanism, that it's like all the programming that you can put in, is capable of attaining, that is the variety, must be greater than or equal to the number of states of the system being controlled. That's a fundamental restriction that you will always have. So that is why it's also hard. Any viable system which can cope with a changing environment, that is what we like to have, contains matching variety in relation to the environment. So you need a model to act upon. You need a restricted filtered set of inputs and assumptions and design decisions. And let me rephrase that, because that's a concept that can strike one the first time one listens for it. So if a system is to be able to deal successfully with the diversity of challenges that its environment produces, then it needs to have a repertoire of responses which is at least as nuanced as the problem thrown by the environment. That is only variety absorbs environment. So you can imagine that you have this kind of system and you are always being asked for features and some other things. So the system, the model that you are trying to produce always needs a way to represent that. That's why computer science is hard, and the kind of inputs that you allow in are much broader than in other fields. So let's say like construction engineering, that it was a field that I used to work to. Computer engineering is harder than construction engineering in the sense that the kind of restrictions of the domain that you are working on are much broader. So for instance, you are not allowing construction engineering to put like a piano every day inside. So that means there is a restriction over the size of the doors. You cannot put a heavy load because there is a resistance that is already put in. There are certain physical variables that restrict that. In software systems, that is not always very easy to specify. So it's a fundamentally harder problem, and you always need this kind of model to act upon. So let me go on. How this connects with software systems. So there is a concept of what's a viable software system. So a viable software system should aim to be able to accommodate change. So you are constantly having changes in the environment. That is maybe features that someone asks for you. Maybe someday you need to produce a Word document template. The other day is Excel. It all depends on how the environment is changing. So your software system should be able to adapt to this and accommodate those changes. When assumptions change, those assumptions are the ones that I'm mentioning, and there are some design decisions involved. It should be also easily comprehensible and divisible. So why is this? You should comprehend the system because it's programmers the ones that are modifying the system always. It's people that are doing this, so you have to make it easier to understand always. That's the only way to cope with a changing environment. And it should be divisible in the sense that you might need to put many people to work on it. So let me borrow some other concept that you might be already familiar from Professor John Osterhout, the author of the book of Philosophy of Software Design. So he kind of grabs all of these concepts from the perspective of complexity. So complexity is anything related to the structure of a software system that makes it hard to understand and modify the system. So that's how complexity manifests usually. If you stop to think for a moment, in all of the design patterns that you might have heard and all of the strategies, all of those try to control and cope for this. So let's take, for instance, one design pattern that is strategy. So what happens when you code some strategy pattern? What you're trying to achieve there, it's being able to cope for a change so that it's like a new case that you should try upon. And on the other hand, you're trying not to make the complexity explode, because when you add this kind of component, you're not like multiplying states, you're just adding states. So you see there is always this fundamental trade-off that you need to accommodate change, but whenever you modify your software system, you cannot do it in a way that the complexity explodes. So what you are always trying to achieve, it's trying to have the complexity at bay, you know. There is always a signature of complex systems, and it's something that you can use as a design criteria, that all software or viable systems, are self-similar. So viable systems, like this one, always contain viable systems inside. So if you think a software system, the cybernetic description that I was giving, it applies in many scales. So when you were taught to write a software, a function, you were told like try to make it only deal with one thing at a time. That also applies to a module on a different scale. So there is some property of self-similarity that is always present in these complex systems and complex systems that are viable. That also happens in the human body, that you have some respiratory system working at the cell level, also at the body level. That's a signature of complex systems that you can modify and are viable. So you should aim for these kind of properties. So if you get 3 words from this presentation, while I'm trying to make you bring with you, you should always be able to make components that you could replace, understand, or divide. Let's try to solve the problem of a scale. What's the problem of a scale? So I will try to take an approach of scale as some change of a design decision. So we need to aim so that a scale change in a software system is handled as any other change. It was a design decision that changed, so ideally we should be able to handle that in the same way. We want to think operating on a scale as a design decision chain. So we know some concept already that has all the properties that I just mentioned that enables to produce a viable software system. And let me try to read some of the advantages. So there is the advantage of managerial development. Time should be shortened because separate groups should work on this word that I'm gonna try to get from you with little need for communication. Product flexibility should be possible to make drastic changes to one. We need to fill the word there without need to change others. Comprehensibility should be possible to study the system one at a time. So what, I will make like a small poll. What do you think is the word that fills in there? Can someone give it a try? What's the word that we should be, sorry?
Module, component,
feature. Feature. Module, component.
Feature.
Anyone else? So exactly, that's modularity. It's modularity. So many times people tend to associate that immediately with microservices. And the real solution for this is modularity. Where did this come from? So there was this seminal paper from David Parnas that is on the criteria to be used on decomposing system into modules that explicitly speaks about it. So it looks like somewhere in between, this word started to be associated maybe solely with microservices. But that's not the case. It's modularity what we will need. So a monolithic code base is in no way implies a monolithic software design. So let's speak about modules a little bit. So we know that modules have certain properties that aim to solve the problem of constructing a viable software system. We have heard many times we need modular code, and we acknowledge, but there are many criteria to divide the code into modules. So you're usually taught to divide, but maybe not all the times people are speaking of how to divide that. And this is the kind of insight that you will get from this very important seminal paper. So the effectiveness of modularization is dependent upon the criteria used in dividing the system into modules. So module decomposition, criteria, or why scripts suck. Have you ever thought why a script really sucks? Like, why is it hard to work with a script? So if you start to work like step-by-step analyzing what is happening, is that usually when you start working on a script, first you understand the domain, and you start to create the components out of a flowchart decomposition of a system. You are not doing a functional decomposition of a system that is based on this very important principle that is the information hiding. So what's information hiding is a principle of segregation of the design decisions in a computer program that are most likely to change. That's one of the criteria that we should be using to decompose a system. Instead of the time, when you need some function, you will need that. That also explains why protocols are really hard, because in protocols you have no other way than to go over certain order of the actions that you are undertaking. That's protocols are very hard to program and very hard to change. That's fundamentally embedded into it. You are basically, and you have to decompose that as a flowchart. So information, there is always a protection involved into this that is providing an interface, a stable interface that protects the remainder of the program from the implementation whose these design details are likely to change. So what's all of Parnas' conclusion out of it? And you can bring this as a general heuristic that it not only applies to architecture of system, but many other things. So we should begin always, ideally, with a difficult design decision or decisions that are likely to change. Each module is then assigned to hide such decisions. So imagine, again, the strategy pattern What are you trying to hide? How to accomplish something? When you use the strategy of what to do versus how to do it, when you segregate like the controller side and the side effects, you're always kind of doing this kind of things, trying to hide that. How that looks into a graphic. So you want to aim for a segregation of design decisions likely to change, accessible through an API. There is this very important word there that is API. So creating an API is not always the easiest thing. You have always to understand the domain, and that's a very important thing. And that's if I would say that the takeaways of this lesson, it's like you have to understand the domain, but you don't always understand the domain. So imagine when you started to code your first like accounting system, you might have started like mutating a database instead of using like double ledger. Why you know the double ledger is the real solution? Because accounting is some domain that has been worked on since the Babylonians and Sumerians. So it has extended the use of time. We already understand that domain. So you should never try to make relations between module implementations but using through an API. But there is this fundamental problem of knowing what's the correct API. So there is always this kind of trade-offs. So you don't need to introduce a network boundary as an excuse to write better code. That's so it's the most important is understanding the domain. So let's speak about Django now in this last part of the presentation. So you'll usually start with a small project from scratch that starts to evolve. So understanding the design decisions that the framework makes for you, it's super important. It's always easier to merge than separate. And there are a lot of underlying things that are happening in Django that you will need to understand. So there is an authentication backend involved, a session storage backend, a cache backend, a database backend, a static files backend, media files. All of these has implications, and all of these will end up affecting your scaling. The first thing that I will give you like a concrete actionable insight of all the projects that we have worked on and the knowledge in the community is that working with Django's templating system for scale is very hard. So that is usually one of the first things that is done for Django and Scale, segregating the UI. That will make you tackle a problem that can become hard, and you will need to solve authentication. So Django's authentication system is great. You have like very updated hashing algorithms, Argon, PKDF. So you will have to tackle that. You will need to adapt that if you want to go for Scale. Let's talk about applications. When you start learning Django, you learn the concept of application. But the problem with applications is that we usually don't understand the domain. So one of the things that we've seen in many like huge code bases is that these code bases have a minimal number of applications or just one. Until you understand the domain, it's not recommended to start creating many applications. I'm not saying that the applications are not correct or take you in a wrong way, but that's the fundamental problem. You don't understand the domain. And you start to have a lot of dependencies that manifests itself as a lot of coupling. If you have foreign keys linking models across different apps, Django migration system will try to infer a dependency graph so that migrations are in the right order. That adds a ton of complexity. There is a lot of big applications where you are not able to untangle the migration sometimes. So there is usually this case of the migration system working on production, but every developer machine has a different permutation of the migrations. So there is usually solutions for this, so maybe you can go for the reference that I will leave you, but there is a way to create like a conflict before it comes to your database, and this is one of the solutions. Then we come to some motto that it's very popular, and it feels kind of a relief or that you found something when you hear fat models and skinny views. So it hears like amazing when it kind of makes sense where you need to put the code, but it usually ends very bad. That's like in very big applications, it's usually the other way around. You want like very lightweight models, just solely focus on the data layer. So you gotta put your logic in some other layer that sits between the data layer and the API. A presentation layer, a services layer. So I would say like, take with a pinch of salt everything that you start learning for these big systems. So what does it mean, put your logic in some other layer that sits between the data layer and the API? So the framework itself has a modularization for the request response cycle. You should not allow your code to be influenced by that. They are trying to solve a different problem than yours. You have a domain problem to solve, and the framework has another problem that it's getting you sending you a request and taking a response out. So this layer architecture that I'm showing is often like misinterpreted in the sense that first it kind of conveys the idea that the request should flow into the inside, and sometimes when you start programming Django, it feels like a relief to have this very well-behaved object where you can get all the things, even the headers, but that's not really recommended. So we will see how to handle that. There is also something very important that is not only where you should be putting your code, but also you should understand what's the knowledge that is involved in calling some other code. So I will explain that. I usually prefer this kind of depiction of the clean architecture that you might be familiar. Let's use this example from this amazing book, Architecture Patterns with Python, that I really recommend you to write. So if you see how they work their code, this is like the entry point. So after you get this into your view, this is one of the things you get. So let's try to understand that. The first thing that you will see there is that this code only is communicating with a services layer. It's completely unwrapping the request. So from this, after the view and beyond, there is no other knowledge of Django. Request stops there. It is also pass-only built-in data types. The knowledge of HTTP code stops exactly here. There is no more knowledge of HTTP beyond that. If you check how the exceptions are cached, they are being translated to HTTP just in that layer. It's only calling another service layer.
I couldn't find that in your Apple Music library.
So then we go to the application service layer. So this layer only knows about the domain model that you will see there. Can you see the code? Is it okay? Well, anyway, this is a bigger version of the same thing. So here we kind of work in the same way. We are only communicating with the domain model. There is no knowledge of Django there. Let me repeat again. You are just communicating with your domain model. So what's one heuristic that you could use to test for a good code? You should be able to take all of your domain code and being able to use it from a command line interface. That's a good heuristic that you could use. Using it for games is very important. It's very clear if you want to imagine the example using a game. So imagine you are writing a tic-tac-toe. You should be able to take all the logic with you. It shouldn't depend at all with Django. So the logic shouldn't be at any point in some view or any other place. So always try to make this hard test for your code. Like, could I be able to run this from a command line interface? The domain model that's called from the other layer, it's a representation of meaningful real-world concepts pertinent to the domain that needs to be modeled. So make yourself this question: can I take my domain model and use it from a CLI? Can I give this domain model to someone that doesn't know anything about Django and he will understand it and translate it to his language? This is how usually big migrations out of the framework work. It's not something that it will occur all the time, but the big migration usually occur that way. You have to take this code, hire a new team with programmers with proficiency in other language, and they should be able to translate. So they shouldn't know about Django. If you cleanly separate this and you're only using built-in data types and not any like exotic feature of the framework, you will be able to achieve that. It's not easy, but that's we are speaking here mostly about heuristics and the best attainable state. let's get into the database. So the database is more important, long-lived, and harder to change after the fact of your application. So design your schema and don't allow the framework to make decisions for you. There are a lot of decisions that Django makes for you that could impact you in the future. So just the naming of the tables, that's something that is a very low-hanging fruit that will save you a lot of time. So modules ideally should only access their own tables, because it's always easier to move in that spectrum. So usually, if you always use like your same tables, then you can move that to some other schema and separate. Then you can go to some other database, or maybe to some other persistence when you need better scale on your database. Always avoid cross-module joins. Neither share tables between modules. Usually when you start to segregate, call it whatever, microservices, it will be very hard to make these joins. However, referential integrity, it's usually advised to keep it, because that's a better understood problem, and there are many solutions for like referential integrity and all of the transactions in whatever other system that you might be using. So pay attention to this. Make also very flat schemas. Always imagine that the easiest predicate is a select. So if you can always solve it with a select without joins, that's good. Maybe you can go to some very, very well-designed schema like a Stripe, and you will understand that, you will see that you will acknowledge that they will be able to answer your queries just by querying one table of one entity. That's something that you could do. Always use true models. That's also some other decision that Django is hiding from you. Django is actually producing that table, but it's usually hidden. So when you use the true model, you can access that. That will not only bring you the advantage of having visibility and being able to put more data over the relation, but that could also ease the queries a lot. So you will pass from the query that it's down to the query that it's up. It will be like very simple. Signals. Try not to use signals. That's a Django feature. So you have always to think, what are the features that you will not have if you move out of it? So limit the use of signals. If you need to, just put it there. Signals is a Django feature that spills all over the architecture. Eventually, you will need to implement some other mechanism like your unboss. Foreign keys, that's not very popular, but that is like really hard to untangle. You might be familiar if you know the comment system. So that's the kind of feature, the Django feature that is used to attach this comment for any model. Caching. Caching, it's always hard, but just let me give you some, as you know the phrase, there are two things hard in computer science. There is cache invalidation and naming things. But if you migrate a schema, the cache model could be from an earlier version, so it's always recommended to cache primary keys. In these very big systems, that usually how it works, but it means that you will also need to implement your own caching system. Remember, variety only absorbs variety. Complexity doesn't disappear, it's just moved somewhere else. So you will have to solve that. So better cache primary keys, and always remember the fastest possible form is this predicate of a select. So that's what it's, what it takes a lot of resources. It's not like fetching the object when you have the primary key, it's finding the primary key. Avoid using Django, the ORM, as the main interface to your data. That can be polemic around it. Django ORM is great, but it has some problem. It's an active record pattern. So if you start to have Django objects.all or some other safe all over the place, I would say that that's a kind of a red flag of how hard it will be to move out of Django. It doesn't mean that we are definitely moving out. We are not like making early optimization, but the whole idea is that whenever you will need that, you leave your software system in the easiest way to accommodate to these new changes. So one approach is to use a repository pattern. That doesn't mean you need to. You can concentrate all ORM usage into a layer like services. This is, however, harder for misuse. So if you do that, you also gain some other optimizations. Imagine that you have all queries all over the place that you need to optimize, where you should be putting all of these like select related, prefetch related. If you concentrate everything in one layer, it's very easy. You just modify that. You don't have to go to every place in your code. And finally, what's the role of tests? So, should I say this? At this point, I would like that you understand that change is constant and an inevitable struggle, and in the end, it's an inevitable struggle to understand the domain. You don't always understand the domain. That's always the thing that you are doing. It's like sculpting something that you start with some brick, and then you start to make some cuts, and the idea is like to make the same thing. Programming in the end is a craft. Like you're trying to mold your thing until the point that it works. So do tests. Designing for testability really means designing for extensibility. You will be able to do fearless refactoring. You will have to refactor a lot. TDD is a design practice first and a testing practice second. So whenever you're writing your test, you will always have this kind of canary or red flags of how your code is just by writing your test. If you have to make this house of cards just to test something, I will check the architecture again. So finally, one conclusion that you will find in the most widespread books, there are no generic software architectures. The really important thing is trade-off analysis. There are no best practices, but hopefully now with these tools of how to think about the systems and how to approach your programming craft, you will have more tools to solve your problem. So thanks, that's the whole talk. Thank you. I will leave you this.